Welcome back. In this section, we'll be talking about right-angle trigonometry. First, before we get into the trigonometry side of things, just a couple of reminders about the geometry part, the right-angle triangle. First is, notice in my diagram that I have here, I have my right angle indicated with a little square, and that for a right-angle triangle, that the side that's opposite that 90-degree angle, that's our hypotenuse. That's the special side that's the longest side of that right angle triangle. And if we're talking about an angle theta that happens to be inside of this right angle triangle, then in addition to that hypotenuse, you'll also have one side that's opposite that angle and one side that's adjacent to that angle. Now, which side is opposite and which side is adjacent really depends on where you are thinking about that angle theta being. So I was talking about theta being the angle at the bottom right, but if I was interested in, let's say, the angle that's at the top, the hypotenuse would still be the same. It would be the side that's opposite my 90-degree angle, but the opposite side would be the one at the bottom, and the adjacent side would be that vertical side. So just to keep in mind here that when we're talking about right triangles, who is the opposite and who is the adjacent side will depend on which angle we're talking about. The other thing that we need to keep in the backs of our minds is that we have, for right angle triangles, the Pythagorean theorem, which is a relationship between the sides of our right triangle. For a right triangle, the hypotenuse squared would be the other two sides squared and added. So if you know two sides of a right triangle, you can automatically find the third side. So for trigonometric functions, these are going to be brand new functions, just like how in the previous chapter we introduced logarithms as a new kind of a function. Here we're going to introduce another new kind of a function, the trigonometric functions, and there are 6 of them. What they'll do is they'll take an input. The input will be an angle in a right triangle, and then the output will be a ratio of those triangle side lengths. And the reason why we're interested in trigonometric functions is that it's going to allow us to solve some problems that we might not be able to do just by geometry alone. So for example, I said here that for a right triangle, if you knew 2 of the side lengths, you could figure out what the third side length is using the Pythagorean theorem. But you might not know 2 out of the 3 side lengths. You might only know 1 side length. And maybe instead of knowing another side length, you happen to know an angle. Trigonometry will allow us to find the other side lengths knowing just 1 side length and 1 angle. And we're going to see a bunch of examples of that in the future. So the 6 functions that we're introducing here, they are called sine, cosine, tangent, cotangent, secant, and cosecant. And for short, sine, S-I-N, cosine, C-O-S, secant, S-E-C, cosecant, C-S-C, tangent, T-A-N, cotangent, C-O-T. Similarly to how we define things with logarithms, where I said, for something like log base 5 of x, that log base 5 was the name of the function and x was the input for the function, much in the same way here, sine is the name of the function and theta is the input for that function. So theta is an angle, and it's being put into this function whose name is sine, and what's coming out would be the ratio of those side lengths, the opposite side divided by the hypotenuse. And we have all of our 6 functions defined in a similar sort of way. For cosine, when an angle theta is put in, what comes out? Adjacent divided by hypotenuse. And then the same thing for all the rest of those 4 trig functions. A couple of things that are to note here. Number 1, for our angle, it has to be between 0 and pi over 2 radians, which is the same thing as saying between 0 degrees and 90 degrees. And that's because we're talking about an angle theta that happens to be in a right triangle. An angle inside of a triangle can't be 0 degrees, which is why we're not including the 0. And also, you can't have another angle in a right triangle that's 90 degrees, because if you did, you would already have 180 degrees, and so your triangle would have more than 180 degrees in it, which again, not possible. So when we're talking about our angles here for right triangle trig, we're talking specifically angles between 0 and 90. That means that we won't be able to do anything yet with things like what is cosine of 90 degrees or what is tangent of 0 degrees. That's going to require us to have another definition for these trig functions. Also, if you're thinking back to the previous section, you know that angles don't have to be just between 0 and 90. You can have an angle, for example, of 270 degrees. And unfortunately, right triangle trig is not useful for that. So that's the reason why, in case you're wondering why there's multiple definitions for these trig functions, it's because in some cases, right angle trigonometry is good enough, but in others, we'll need an expanded definition that will cover cases like, what about negative angles? What about angles that are less than 0? What about angles that are more than 90? And we'll see all of that going forward. A couple of things that I just want to mention about these functions themselves. You'll notice the way that I've written them in this little chart that I've got here, that these functions are, the ones that I've put in little boxes here, are reciprocals of each other. That for sine of theta, it's opposite over hypotenuse, and for cosecant of theta, it's hypotenuse over opposite. So if you know sine of theta, then cosecant is just the reciprocal. And same thing for secant and cosine, they are reciprocals of each other. And tangent and cotangent, they are also reciprocals of each other. It's also true that you could take just sine and cosine and rewrite the other four functions in terms of them. So for example, if you took opposite over hypotenuse and divided by adjacent over hypotenuse, and then did some simplifying, you would get opposite over adjacent, which is the same thing as tangent. So if you take sine of theta over cosine of theta, you get tangent of theta. And you can define the other trig functions, secant, cosecant, and cotangent, also in terms of sines and cosines. One other thing to point out here, and you might have noticed this with the names, that the names kind of come in pairs as well. There's sine and cosine, there's secant and cosecant, there's tangent and cotangent, so they're kind of pairs that we have here. Those three functions, cosine, cosecant, and cotangent, those are called cofunctions. Cosine is a cofunction of sine, cosecant is a cofunction of secant, and cotangent is a cofunction of tangent. We're going to see in a little bit that there is a special theorem relating a function and its cofunction, and we'll see that in just a little while. One last thing that I want to mention before we start working on a problem is, and again, it's the same thing that I mentioned with logarithms, about that the name of the function is, in this case, sine, and theta is the input for the function. The name of this function is cosine, and theta is the input for this function. I'm mentioning that because the same sort of problem that we often see with mistakes being made with logarithms sometimes also gets made with trig functions. If you're remembering when I said for logarithms that if you were interested in something like log base 2 of 10 over log base 2 of 20, that because the 10 and the 20 are the inputs for these functions, it's not possible for me to cancel the 10 with the 20 and turn them into a 1 and a 2. That would be desperately and dramatically wrong. And much in the same way, I also couldn't, if I had log base 2 of 10 over log base 2 of 20, I couldn't just cancel the log base 2's and say, oh, it's 10 over 20. That would also be wrong. And that's because the log base 2 and the 10 are one single entity. Log base 2 is the name of the function and 10 is the input. Log base 2 is the name of the function and 20 is the input. The same sort of thing is true for trigonometric functions as well. So typically I might see people saying things like this: sine of 30 degrees over sine of 15 degrees. People might feel like maybe we should be able to cancel the 30 and the 15, and of course that's wrong. Or perhaps maybe we should be able to cancel the sines and we're left with just 30 over 15. And again, that's wrong for exactly the same reason. The sine is the name of the function and the 30 degrees is the input, so that's really one entity on its own. Same thing with the sine of 15. Sine is the name of the function and 15 is the input, so again, that's one single entity on its own. It's not two things that are being multiplied together, which is why we can't cancel the sines out or cancel the 30 and the 15. And that's because 30 is not a factor of the top. 30 is what's going inside of that sine function. Sine is not a factor of the top. Sine is the name of the function that's on the top. So for this first problem, we've got ourselves a nice little right triangle here, and we want to come up with the exact values of all of our trigonometric functions. And I know I've said a bunch of things about exact values, but I'm just going to mention it again here that when I say exact values, those are not values that we've run through a calculator and rounded off. I know that for some people in the past, they may have taken an earlier math class where trigonometry was introduced, but it was introduced basically in a calculator sort of context, how to use your calculator to churn out trigonometric functions. But I'm not so interested in what your calculator tells me. I'm interested in you being able to find these values yourself. So if we just rely on our calculator and give me decimal answers, that is not what I'm interested in here. I want the exact values of all of my trigonometric functions. So you'll notice here that we've got our angle theta that's in this right corner, and that means that the 4 that we have here, that must be our opposite side. That's opposite that theta. And that 2, that's the side length for our adjacent side. And the one side that we don't know is the hypotenuse. But this is where we can use our Pythagorean theorem. We know that the opposite squared plus the adjacent squared should be equal to the hypotenuse squared. Our opposite is 4, so 4 squared, or 16. The adjacent measures 2 units, so 2 squared, which is 4. And we can find out that our hypotenuse squared is 20, and so our hypotenuse itself should be root of 20. Now, of course, remember, as always, anything involving roots needs to be put in simplest terms, and root of 20 in simplest terms is 2 root 5. And that's, of course, because root of 20 is the same thing as root of 4 times 5, or root of 4 times root of 5, which is 2 times root of 5. Okay, so now we found our 3 side lengths. We have our adjacent, opposite, and a hypotenuse now. So we're ready to give all of our 6 trig functions. Starting with sine of theta. That's opposite over hypotenuse. Opposite side measures 4. Hypotenuse measures 2 root of 5. And then, of course, we need to simplify this. And in simplest terms, 2 over root of 5, that's not in simplest terms. Remember, we don't want to have any roots in the denominator, so I'll rationalize that denominator, multiplying top and bottom by root of 5. And I have 2 root 5 over 5. And while I'm here, since I have sine, remember that for sine of theta, that the cosecant would be its reciprocal. So I know once I've got sine, I can easily find what cosecant is. Cosecant should be the reciprocal of that. We found sine of theta was 4 over 2 root 5. So cosecant would be 2 root 5 over 4, which in simplest terms is root 5 over 2. And now we've got 4 more functions to find. So I'm just going to underline these so I don't lose them in the shuffle here. So I've got sine of theta and cosecant of theta. We've got those. And now we just need to find cosine and secant, tangent, and cotangent. So I'll do cosine of theta. And we know cosine is adjacent over hypotenuse. That's our definition for cosine. The adjacent measures 2, and the hypotenuse measures 2 root 5. That's 1 over root 5, which, once we've rationalized our denominator, that would be root 5 over 5. So multiplying top and bottom by, so taking this, multiplying top and bottom by root 5 over root 5, and you've got now root 5 over 5. So now we know cosine of theta is root 5 over 5. We can also use that to find secant of theta. Remember that secant is the reciprocal of cosine. Cosine was 1 over root 5. So secant should be the reciprocal, root 5 over 1, which is root 5. And let's see, what's left is tangent of theta, which is opposite over adjacent. Opposite measures 4, adjacent measures 2. So tangent of theta is 2. And then finally, we've got cotangent of theta. Remember that tangent and cotangent are reciprocals of each other. So if tangent is 2, then cotangent should be a half. And there we go. We've got all 6 of our trigonometric functions written out, and we have the exact values for all 6 of them. One thing I do want to say just before I move on to the next slide, and this is something just to be careful about when we're writing, remember that for a function needs to have an input. So if I were to write, for example, here, if I just said tangent equals 2, that's not technically correct, because tangent is just the name of my function, and you're saying here's a function that I haven't put anything in, but somehow I'm getting 2 coming out of it. Remember that a function needs to have an input, and here the input is the angle theta. So if we want to be correct, technically speaking, we need to really write tangent of theta is equal to 2, because if we just said tangent equals to 2, that's actually not correct. Much in the same way that if you were saying that a function f of x was x squared, and I said, what's the y value when x is 2, and you just said, oh, f is 4, that doesn't really make a whole lot of sense, because again, you're saying here's some sort of a function that had no input somehow having an output. Functions need to have an input, and for trigonometric functions, that input is the angle, in this case theta. Okay, let's do one more before we have ourselves a little bit of a brief pause. So we've got a right triangle with an angle theta, and we know that sine of theta is 2/7. So the first thing that I'll do here is draw. Since I'm talking about a right triangle, it makes sense for me to draw a right triangle. And if I'm drawing a right triangle, I'll need to indicate the angle. That's the right angle. And I'll also need to indicate my angle theta. And I can put it wherever I'd like, but I'll put it here. And the other thing that I know is that sine of theta is 2/7. And I know that sine is opposite over hypotenuse. So that means for this triangle, the opposite side to theta should measure 2, and the hypotenuse should measure 7. So I will go and label my triangle with the two sides that I now know. The opposite side is 2, and the hypotenuse should measure 7, which means that there's only one side that I don't know, which is the adjacent side. Okay, so that means, as before, I should use the Pythagorean theorem to find out what the adjacent side is, so I'll do that up top here. I have the opposite side squared plus the adjacent side squared is equal to my hypotenuse squared. And if you were to simplify this, this would give you that the adjacent side squared is 7 squared minus 2 squared, or 49 minus 4, which is 45. So that means that the adjacent side is the root of 45, which in simplest terms, that's 3 root of 5. Okay, so now we've got everything we need, and so now let's fill in what we have. I'll do the easiest one first, which is, we know that sine of theta is 2/7, and we know that cosecant is the reciprocal of sine, so actually cosecant of theta, we could have found that out right away. That should be 7/2. So now I just need to find the other 4 trig functions: cosine, secant, tangent, and cotangent. I'll do cosine. Cosine of theta, that's adjacent over hypotenuse. That is 3 root of 5 over 7, and that's in simplest terms, so there we go, we're good. And secant should be the reciprocal, 7 over 3 root of 5. And of course, we'll need to rationalize that denominator to give us 7 root 5 in the numerator and 3 times 5, or 15, in the denominator. So we've got now cosecant, cosine, secant. We just need tangent and cotangent, and then we are finished. Tangent is opposite over adjacent, which is 2 over 3 root of 5. We'll rationalize by multiplying top and bottom by root of 5. And that gives me 2 root 5 over 15. And then finally, for cotangent of theta, that would be the reciprocal of tangent, which instead of being 2 over 3 root 5, would be 3 root 5 over 2. And there we go. We have all of our other remaining trig functions. We found cosecant of theta, cosine of theta, secant of theta, tangent of theta, and cotangent of theta.